think you can call him.
Okay.
You can hear him.
Yeah, so the current lecture is about the formation retract that increase functions. So let me just give a motivation. So in several situations we will have a we're going to have the following. We have a manifold and we want to estimate its topology. So we would like to be able to deform, to take a retraction of the manifold and that into the thick part. So first, we will remove something that we don't know what to do with, and then we would like to define a deformation retract to a subset of the manifold. So at each point, we will want to define a direction that increases the injectivity radius. So here we don't know, but here we go this way, here we go this way, and at the end we will be in the thick part. So we need some procedure which will allow us how to choose the direction in which we flow in order to increase. And then we will be in the thick part, and the thick part is not as nice as its boundary can actually be complicated. So, and then we suppose this is a thin part. The thin part may have thin part consists of a union of convex sets, as we will see, but maybe they are very sharp. And what we would like to do is to take a neighborhood of the thin part. So if you want to complement the shrinking of the thick part and to work there. So this is again, we want to be able to flow from here to here to define some deformation retract like this. So maybe just let me write the definition. So if you have a set A, then it's for any t, AT, it's the t neighborhood. It's a set of all, it's the union of all balls of radius t around point in A. So it's the t neighborhood. And A, like this t, is the t shrinking. The t shrinking is just, if you want, it will be S minus the neighborhood of S minus A. That's the t shrink. So we would like to shrink the thick part of it, right? In order, or to take a neighborhood of the thin part. So that's we would like that. So so sometimes we are given a family of functions, and we want to define. We want to find a deformation. Deformation retract that increase this function. So, example. We want to, so if the function can be the displacement function, the thick part you want m is epsilon, or it's this is in the universal cover. It's an example of a submanifold which is given by the condition that the injectivity radius is at least epsilon over 2, or the displacement of a non-trivial element is at least epsilon. But what does it mean? It means that the family of functions, which are displacement of element in the group, all of them are at least epsilon. Or if you want, at any point you have the function which is the shortest loop in every homotopy class, and you want it to be so it's given by the condition that d gamma is at least epsilon for every gamma in gamma. So we see we want a certain function to be large. And the same for shrinking. Shrinking is the same but for displacement function. So this is one example. Another example, if you write S is, or if we have X is the union of Xi, and suppose that Xi are convex, and suppose we have M tag tilde is the complement, so it's S minus X, then it's shrinking, epsilon shrinking is defined by the property that intersection of we want to be far from all the displacement function to Xi is at least epsilon. I have to. This is displacement function. dA, the distance function. It's the distance from this is how I denote distance function. So this is another example. So if I want to be far from some set, which is it's a union of convex set, then it's another. Okay, this is what we would like. So in the last lecture, we actually had a way to do it. So let me recall. So why not defining, say, like in the last lecture, the previous lecture. We define a psi of X to be sum of f of we're given a family of functions, let's call it f. So let's see f of phi of x. So phi run over f. Like before, phi could be a displacement function or distance function. Why not do this? Where f was the following function. And then if we flow along until psi is 0, all this function will be at least epsilon. And so why not do that? The problem is the following. So let me write more slowly. Let M be a manifold. Psi from M to R, a function which is smooth on psi less than b greater than a, and the gradient of psi is not 0 on that set. And b, suppose a could be infinity, minus infinity or minus infinity, it doesn't matter. Because I think then there is psi be a proper function, also proper, but then there is a deformation tract. From okay, b could be infinity from psi greater or equal to b to psi greater or equal smaller or equal to b to psi smaller or equal.
It's smaller or equal to b.
Yeah, so b could be infinity if you want. In the yeah. Suppose psi is positive function. So a is finite. A strictly less than b, and bigger than minus infinity, and b could be infinity. But this is more step. But what is important is that the gradient is not zero. The gradient doesn't vanish on the set, but also on the boundary where psi equals zero. If the gradient vanish on the boundary, then it doesn't move. The standard example, it's not how to find. And in our case of this, the gradient of psi will be zero on the boundary. So we cannot do that. In the previous lecture, we didn't really care. We just define a differential tract until we are close enough to the thick part. Now we want precisely to land on the boundary of the thick part because this is something that we can understand. If we just enable with it, we don't understand. We want exactly to reach to the thick part. So this is why this doesn't work. We cannot apply this in our case. That's a motivation to what I'm going to write, because I'm going to write a complicated lemma, which will go too complicated, and I needed to give a excuse why I don't do this, and why. And okay, so this is so okay. Let another definition. Let's write a few definitions that we need. A family of sets sets, say xi, is called locally finite if every compact set intersects its most finite and negative set. If it intersects every compact only finitely many times. Okay, this is it. Now, a family of positive functions or non-negative functions denoted by f is the family of functions phi, I and I is locally finite if for every value t the sets phi less than t I in I is locally finite. Now only any point if you want, only find many functions get the value less than t at any point. Okay, and another thing which is different from the previous lecture. In the previous lecture, we had this function which we wanted to the value of this function was going down, and now we want to go up because now we work with really the displacement function or distance function. We don't put any f was decreased. Okay, this shouldn't be confusing. So just want to remark this. Okay. What else do I need? What is a smooth function? So my function will be defined on a manifold with boundary. So if you want a function is smooth, so let O in S be a submanifold with boundary. And you have F from O to R. It's smooth if gradient F is continuous. And gradient F in every interior point is well defined. On the boundary, what is gradient on the boundary? It is the direction with respect to which the directional derivative is maximal. And also, it's not a unit vector. You look in which direction the directional derivative is maximal, and what's the value of it, and this will be the gradient. And you want it to point into the manifold. And then you call it the gradient of it. So this is the gradient. Is it okay? So I have functions, so at every interior point I can just differentiate. But on the boundary, I look at the direction on which the directional derivative is maximal, and this will, like that's how I define the gradient, and I want it to be well defined and continuous. Just a mark. Let's also say that T is a critical value for phi if I look at phi bigger than t and take its closure, this is contained but not equal to phi greater or equal. Then it's a critical value. And it's actually mean that T is a local maxima for phi. There is some point that the value is T, but nearby there are no bigger values. So this is a critical value. So I want to avoid critical values. I don't like it. Okay. What else? We also want to define we have a family of function phi, or f is a family of functions, and we define the f bigger than some value t, by definition the intersection for phi f of phi bigger than t. So if t is not a critical value, then I could write greater or equal and forget the closure. So, okay, now the lemma. Another thing, another definition, sigma x t, when we value t, will be the set of all phi in F, such that phi of x is less than so if the phi were displacement function, so this is the generator of the group in the Margulis lemma. So that's but for me, phi could be either displacement function or distance function from complex sets. So and this lemma will apply to both situations. Okay, now I can write the lemma, and you will see it's the length of the lemma is the same as the length of its proof. So but it's okay. Once it's written, it's not a difficult lemma, and it's very precise. So let's call it lemma 3.2. Needs a name. Okay. Consider a submanifold with boundary y inside x. Sometimes y will be inside s. S is the symmetry. So sometimes y will be all s. This will in the non-uniform case, y will be all s. In general, y is after I remove this bad singular sets of short geodesic. So this is it's an open. Oh, it's without boundary actually. Submanifold without boundary. Submanifold without boundary. Okay. Y is okay. Let f be a locally finite family locally finite family of continuous function of continuous non-negative real valued function on Y. And this could be displacement function, or for us, we use only displacement function or distance from a set. So they don't have to be smooth. Like distance function is not smooth. It's smooth only if you are it's zero when you're in the set, and suddenly it's so. But it's smooth outside the set, and also displacement function is not smooth where the minimal displacement occur. Assume every phi, every phi is smooth on phi greater than 0. And phi greater than 0 is a submanifold with smooth boundary. So this is what it is. So, for instance, if you look at displacement function of a distance function, this is a set xi, and you look at the distance function from each side, then it's not smooth because here it's identically 0 and here it's not. But if we avoid this set, here it's smooth. Also, if we consider the boundary, the gradient in the boundary is pointing orthogonal to the boundary. Okay, let L be the F thick part, the zero thick part. No, it's not. This is by definition intersection of all phi greater than 0. So you see, so it's not the same as the intersection of phi greater equals 0. Phi greater equals 0 everywhere. But I don't want to take interior point of that sense. Just, okay? And let beta from 0, 3 epsilon to R positive be a continuous function. Okay. Assume that epsilon is not a critical value. Value of any phi. So, and this is a good assumption. Epsilon at the end, epsilon will be the Margulis constant. But if it happened to be a critical value of one of them, then we deform it a bit. So it won't be. There are only countably many functions, each of them has only discrete set of critical values. So that's not a big assumption.
Statement. Now, as of now, it's not the Margulis constant.
It's not. This is general, very general situation. So yes, this is very general lemma. S could be any.
You can take any epsilon which
Yeah.
is not a critical value.
Yeah. But at the end, it will be the Margulis epsilon up to small deformation. Okay. Assume that for any x, y, there is a tangent vector nx. This is tangent to s t x s, such that nx and the gradient of px is at least so any phi belong to sigma x 3s. Okay, that's for any x I would like to have a direction. Any x, I would like to have a direction. So this is a normalized vector. When I write hat, it's normalized vector. It's unit vector, such that the directional derivative of every phi is bounded below by this function that is given. So there is some direction. And then the conclusion, then there is a deformation retard from L, recall it was where the functions were all non-negative, the closure of where the function is, or the function is positive, to the epsilon thick part. F, this is the epsilon thick part with respect to this function. So, and moreover, if the family was a gamma invariant for some group gamma, and moreover, if the family is gamma invariant, and gamma is some discrete group, yeah? Gamma is a discrete group, gamma G, it will be a lattice, but a discrete group. So if the family is gamma invariant, what does it mean gamma invariant? It means that if you have a function and you translate it by gamma, you get another function which is still in the family. Means that, this means that phi gamma belongs to F for any phi F and gamma in gamma. That's what it means. If the family is gamma invariant, then the deformation retract then let's say R is gamma invariant and induce deformation retract from on the quotient space from L mod gamma to F at least epsilon mod gamma. So you can go to the manifold and okay. This is just everything. So we will define explicitly, we will write explicitly a formula for the deformation retract, and you will see that if the family of function was gamma invariant, then the explicit deformation retract is gamma invariant, and therefore it induces the deformation retract. Okay, so writing the lemma was the difficult task, and now we'll just write what is the deformation retract. So the idea is that we will define a vector field on which the flow on this vector field will be the retraction. The problem is that now we cannot find a single function, psi, like before, and the vector field will be the gradient of psi. But we write explicitly, we still can write explicitly a vector field, some vector field. So proof, we will define a vector field, continuous vector field, continuous, the flow on which will be the desired deformation return. Okay. Still takes a long line to write the vector field. So here it is. The vector field at the point x will be, okay, first ignore this. I'm writing something, but avoid it. Oh. Yeah. Before I write it, let me just define that delta, the point x, be the minimum of phi family of phi, the minimal value. And phi is infinite family, but for any value there are only finitely many that lower to this. So this is well defined. If you want, this is the injectivity radius. Delta is the injectivity. This was explained before. I'm going to need it. And we want to flow. So we call, maybe I should have, we want the flow, we want the formation retract to the set delta bigger than epsilon. That's now epsilon is constant and delta is a function. Yeah, but we want it to, we want the formation retract to this set. Okay, so here it is. The vector field is defined by square root. Just ignore this element. Okay, I want this to be positive, so I take the maximum between 0. This is just maximum, not this or this. I want to be able to take square root, it's a real value function, but just ignore this at the moment. This will be just correction times sum. Oh, I'm very sorry. Forgive me. I still cannot answer. I need one more some more population. So given sigma inside my family, let given x and sigma, which is a subset of sigma 3 epsilon x. The reason is that it's the same sigma from here. Otherwise, what I want to define, let f hat of sigma in simulation f hat of x and sigma be the unit tangent that maximize f hat dot gradient phi the minimum of this where phi belongs to 6. So sigma is a finite set. I look at I want to look at the direction in which the directional derivative of all of them is I look at the minimal direction derivative. For each direction I look at the minimal derivative with respect to this function, and then I look at the direction that for which this is maximum. I want to choose the best direction that increase all these functions. So this is the best direction. And also define beta, which depend on sigma at x to be the value. To be the value of minimum of beta of phi of x, again, phi is sigma. Okay, sorry, I need this, but modulo this definition. So, if you fix sigma, this f hat is at each point is uniquely defined, because this is basically because of the Euclidean sphere is uniformly convex. So there cannot be two directions which if there are two directions which are increase the gradient for each function at least by something, and the middle of them is better. Yeah. So it's well defined, and therefore f hat of the set is, when the set is fixed, this is changed continuously with x because it's well defined, and this is the value that we need. And just let's just write it. Yeah, it's a bit technical, but we need something like this. I hope it's this is the most technical thing. So observe that f hat of x sigma times the gradient of phi, so phi for any phi in sigma, this is at least the minimum over phi inside sigma of f hat x sigma gradient phi, of course, and this is at least a minimum of phi in sigma of beta of phi x, and this is exact by definition beta sigma of x. Just observe that for any phi this is at least this. So we found a direction now that changes continuously with x. For every set, for every finite set, we find a direction that changes continuously, and the displacement, and we know how much it increases, at least how much it increases every function. So this is what we needed, and now we can write the vector. Now we can write explicitly v hat the point x will be given by square root of 2 epsilon minus delta time sum over all sigma all finite sets of 3 epsilon minus the maximum of phi sigma of 5x. Again, we want this to be by epsilon. Oh, I need more space. I don't want it to look so. I don't want it to look so long. V in square root of 2 epsilon minus delta of x and sum over all sigma of 3 epsilon minus minimum p in sigma p x like the epsilon to state 0 all this time minimum over phi not in sigma of phi of x minus epsilon the bones are so okay times f hat x sigma divided by beta sigma. Okay. This is the way. So, yes, that's a vector field. So, but it's explicit vector field, and I'm going to explain why it's doing the job. So you see, I take a linear combination of direction. For each sigma, this direction changes smoothly. Now, first, if I choose x, just ignore this factor. Ignore this factor at the end, I will tell you why. But if you, so I look at in all sigma, all finite sets inside my family. It's finite. But you see, all of them must be contained inside this term guarantee. This is the way it's term guarantee. No?
Yeah, that's right. Yeah.
Guarantee that I'm considering only sigma inside sigma x 3 epsilon. Because if sigma is a right?
That's right.
Right? Because if sigma is bigger, then some phi in sigma gets the value more than 3 epsilon, and we get here 0. So we consider only. So actually, this says that this same is finite in particular. We're only considering that. This term guarantees that actually sigma contains sigma x epsilon. Because suppose that there is an element in sigma x epsilon which is not in sigma, then this element is not in sigma, and it gets you a value less than epsilon. So again, we have 0. So you see, this is the set that really interests us. And all the sets that we are summing off contain it. So we sum over finitely many sets that all contain these sets. And now you see, we have, this is really a continuous vector field. Now, if you yeah, so if I want to look at the directional derivative, I want to look what happened to a specific phi. So given phi, and all the phi's that interest me are phi on which the value at x is less than epsilon. So phi is in sigma x epsilon. We want to look at the gradient of phi times this v. So this is v at the point x. I claim so all the sets I'm considering contain phi. So so each set give me a direction with some weight. But all these directions are good for phi. All this direction will increase phi because phi is inside all the sets I'm considering. Okay. Given phi, I claim for any sigma in the sum, the gradient of phi times f x sigma is positive. This is because this contains okay, but I claim I want to say that it is at least something. look, consider only the set, only the set. So I still have time, right?
Yeah, you have 35 minutes.
Okay, good. Consider the set, only the set, sigma x 2 epsilon. Only this set. And then we see the first term is at least 1. The first multiplier there is at least 1 because all the functions give at most value 2 epsilon. So it's 3 epsilon minus 2 epsilon, at least epsilon. So this is at least 1. The second set is again at least 1 because if something is not there, then it gives more than 2 epsilon. So this is at most 1. So we see that the gradient of phi times v is at least one. It's at least square root of what's left there. At least this. Because because the way this beta is defined,
So that's
it will be at least beta, and then I divide by beta, and then I get. Okay, so it means that if I flow on V, the flow on V increase phi by at least this amount, i.e. the flow on V increases phi at least by this square root to epsilon minus delta. Okay, and now I tell you why did I choose this square root of 2 epsilon. So I want to define a flow that after 2, if you compute, okay, the intuition was this. You see, when you throw a stone, it stops at some point. And if you calculate the speed of the stone, is exactly square root of twice the distance from where it stopped. So so we want the flow that stopped exactly at the boundary, but it reached there. So the conclusion is i.e. the flow that takes time, the flow for square root of 2 epsilon time unit defines the deformational tract. It is the deformational tract is the deformational tract to delta equals 0, which is exactly the thick point. Okay. So this is the technical lemma. So I had to do it. We need something like that. Yes, that's the. But okay, this is done. And the same lemma we will apply in several situations. And whenever we apply it, everything is verified easily. Whenever we will apply it for displacement function when we want to flow to the thick part, and then we will apply it for distance function. And the only thing we have to check is what is this direction n, and what is this function beta. But that's modulo that we are fine. And now I can give you maybe the strategy. Or the question about this, or fine. Yeah. Okay, so this is the lemma. So in the next lecture, I'm going to apply this lemma, so I will come 5 minutes before and write the lemma on the board, because, and then we will see that we can use it. But what is the strategy now? Let me explain the strategy, not for the, there was a non-uniform case and there was also a uniform case. The strategy for proving theorem 1 and 2. So one was, if you remember, that every so maybe I'll write theorem 1 and non-uniform arithmetic manifold, S manifold, is homotopic to D alpha volume M simplicial complex non-uniform arithmetic S manifold M homotopic. So this is one theorem that I'm going to prove, and theorem 2 is that any uniform for any uniform S manifold, any compact S manifold, there exists a D alpha volume M simplicial complex such that pi 1 of M is isomorphic to pi 1 of R. And here we assume S is not 3 cases. S is not H2, H3, H2 cross H2, and SL3 on SL3. These cases, we don't know. I mean, okay, actually we don't need to assume that. Yeah, this we know. Just in the proof we assume that. H3, it's not true, and in these 2 cases, just the proof. So what is the strategy? There are several steps. So now we have all the tools to do the formation return. Strategy is step 1. Define N tilde to be the union of mean gamma, like before I take some power of gamma, over all gamma hyperbolic, such that the displacement of gamma is less than f. So I will explain it again. So this is the singular subset, singular submanifold. This is the bed submanifold. In this picture, this will be A. Yeah? And whenever I write something in the universal cover, I mean that N is N tilde modulo gamma is there. So this is a singular set that we don't know what to do with. And this assumption, the assumption So by the way, so in the non-uniform case, n will
Not
be
quite modulo gamma. No,
sorry.
Not quite modulo gamma, right? N theta modulo gamma or something.
It's not modulo gamma, but
Yeah,
no,
something
it is
generated by
okay.
small gamma.
Yes, but this is still okay because n tilde will not be connected,
Right.
but it will be gamma. But it's still true that it's
Because some of them,
it's
it doesn't really matter. Really.
yeah. You can take a connected component and then just let it what preserve it and then you can write you can write it like this also. You take connected component.
Connected component. That's
Oh, by the way, also for later, like for Lego, when I write this, I mean connected component. So in theorem 1, the assumption implies in theorem 1 that in theorem 1 that n is empty actually, n is empty set. In the non-uniform arithmetic case, there are no singular submanifold. This will follow from what I said. I will remind it. In theorem 2, we had these assumptions. It would that codim of n is at least 3. Again, all what I say now I will explain, but I just want you to have the strategy in mind. So in theorem 2, what we will have is that the codimension of n is at least 3. This is why we need this assumption. And why is it good? And this implies that the fundamental group of m minus n is the same as the fundamental group of m. When you throw out of the manifold something of codimension 3 or more, you don't change the fundamental group. This implies that the fundamental group of m, which is gamma, is isomorphic to the fundamental group of m minus n. When you throw something of codimension 3, you don't change the fundamental group. Because any two loops you can do, if they're homotopy is something two-dimensional. If you want it, if you touch this codimension 3 submanifold, you can push it, but it won't touch. You have enough direction to push it. So this is doesn't change the homotopy. So this is one thing. Then we apply the lemma, applying this second step is applying the deformation retract lemma lemma 3.2, which I said, we get a deformation retract out from m minus n to m, the thick part. So this is one thing. So now we're in good shape because the thick part is thick and we can do good cover. The problem is that, like in the previous lecture, I took a good cover and I didn't care if it's covered more. Now I don't want it to cover more because I understand I don't want it to cover more, so I'm in a big trouble. So the question is how to construct a good cover for thick part. That's the question. And here I need some information about the thick part. So, okay. So the idea is the following. So let me just type something. The thick part, the thin part. Let's say the thin part is is a union over all gamma minus identity of the set where G gamma is less than F. This is a union of convex sets. And it's a locally finite union. But still, it could be complicated. It's not. Each of these sets has a smooth boundary, but maybe it looks like that. You don't know. And maybe there are a lot of them. So we want to take a small neighborhood of this. We want to take a small neighborhood of the thin part. So if you want, you take some shrinking of the thick part. So why is that? Okay, before I take that, I will explain why. Because we want to cover the thick part by balls. But you see, if I have these sharp things in the thin part, and I put a ball here, and the second with the thick part, it won't be contractible anymore. And even if it is contractible, the intersection of two balls may not be connected or contractible. Yeah. So if I take a neighborhood of it, I will take some neighborhood, then I will not have at least that formula. You see, now I can safely cover this by this. So this is we will take a shrinking, let's say, delta shrinking, or let's say delta is some parameter dependent, or epsilon, let's say epsilon over 100 shrinking of m greater than equal to. So to shrink the thick part is the same as taking neighborhood of the thin. So then we walk there. Still we have a problem. Still this will not okay then when we do that you want to say that there is a deformation retract from the thick part to the shrinking. Then we use the deformation retract. We use the lemma again now for displacement. So we here use again the deformation retract lemma 3.2. Okay. Okay, now it's not enough. Step 3. So we still have a problem because suppose now we want to when you do good cover with balls, you are happy because balls are convex. An intersection of convex set is still convex, and a convex set is contractible. That's why to use ball is good for good cover. Now, even each ball will be contractible, it will not be convex anymore. You see, even if you use small balls, when you intersect it with the thick part, they are not convex anymore. So how to guarantee that they're still contractible? So the idea is to take another neighborhood. So this you will have You will have another. The idea is to take another neighborhood, which is much smaller neighborhood, and now you want to cover the original shrinking. You want to cover the complement of. You don't. This is something you don't see, but you still want to construct a simplicial complex for the complement of this. But the center of the balls will be outside this. So when I first told it in a lecture at the Hebrew University, then Alex Lubotsky suggested to call this the fat and the fat and the dress. So this is the
dress.
yes. So this is the fat and this is the dress. So you want to cover the complement of the fat, but you're using ball that the centers are outside the dress. So okay. Instead of writing, I will take the picture. So you see, you have something which is fat, and now you put a ball, and you know that the center of the ball is not close enough. It's not. There is some distance. Then look, the ball is not convex. But still you can contract everything to the center of the ball. This is what you do. And if you have intersection of ball, you can still be able to contract. That will be there. So this will be, I don't know how to write it, but we'll do the two steps that we take shrinking. One is the real shrinking that we want to cover, and the second is just where we want to center, and then everything will go. And okay, so I think this talk actually I finished what I wanted to say. So if you want, I can answer a question or yes.
So this is not convex. We say something star shaped.
Yes.
Star. I mean.
Yeah. Exactly.
Exactly. Yeah.
Yeah. There will be a star shape. So
you can.
So yeah, maybe I should say that. So the other deformation retract that we are going to use are for star shaped sets. So let me write some definition. Actually, it's good to write it. So let's write. So a set, or let A be a convex set, and let B be a set containing A. We say that B is star shaped with respect to A if the segment B projection to A is in A for every B in B. So let me draw the picture. So you have a convex set A, and you have some set which is not convex. This is B. And it's star subset if these segments, for any point I look at the projection, and it's always inside. So this is subset. And then you can prove the following. Let me write the lemma in the generality that we will need.
Yeah, the segment is in B.
What?
Segment is in B.
Is in B. Yeah. This segment is in B. Thank you. Thank you. once you write it, it's obvious, but it's useful, and we will use it for this type of argument. So lemma, suppose A is convex, and A is contained in B1, which is contained in B2, where BI are star-shaped with respect to A.
Yeah, I was confused. It's PAP. You have to have another point of the projection.
It's on A.
Projection to the nearest point.
Yes.
Oh, nearest.
Yes.
Yeah, this is the nearest point projection.
Okay.
So now, suppose you have 3 sets. Then there is a retract from V2 to V1, and there is a retract from S minus V1 to S minus V2. So let me just just draw it. Now you have 2 stars. They are not star-shaped with respect to each other. So you have set A in the center. You have 1 star. And you have another star. Okay, and then you can retract. This is B2, this is B1. You can define a retraction from here to here. Why? At any point, I look at the projection here, but I flow only until here. From any point, you flow in the direction of the projection. And you can also go backwards. So that's it. So this is another type of information retract that we will use exactly for this type of problem.
So, would you explain that step 2, step 3? Like, so if you just took a epsilon by that 100 shrinking, it wasn't working, right?
Sorry?
In that state,
Yeah.
when you took a epsilon by 100 shrinking of the thin part,
Yes.
the thick part, it wasn't working because of the basically convexity might be lost or something.
Yes.
When you cover,
Right.
go for good cover. But then,
Yeah, I didn't really explain how. I will explain. At the moment, I still didn't explain how am I going to use it. So, yeah, okay. I need to tell you something. So, yeah, there's something to prove. It's not this is just a lemma that we will use. I didn't say that it's not obvious how to use it. Yeah, there's something to prove. But we will do it.
Perhaps you might eventually want to take, given a dimension n, you might want to take epsilon over something raised to n or whatever.
Yeah.
Depending on n.
Of course, this 100 is.
100 was some to some.
Yeah,
some
100
to
is
some
some big
dimension,
number
but
which depends.
given n, you could just say epsilon
Yes.
by something depending on n,
Yeah,
and
yeah.
that will work.
Yeah,
That's
yeah.
the point.
This 100 is depend on the dimension. Yeah.
Yeah.
I will explain this. I will have time to explain everything. I just
Yeah, exactly.
now I just today I just told you the tools and hinted some hints of how we're going to use the tools. For example, to use this lemma 3.2, we will use, of course, Margulis lemma, and we will use the action of the boundary of the symmetric space. And to use this lemma, we will use something like what I described here, but I will do it formally. I will explain it formally. So, yeah. So, one question.
Okay.
ನನಗೆ ಸ್ವಲ್ಪ ವಿಜಯನಗರದಲ್ಲಿ ಓಕೆ ಬುಧವಾರಕ್ಕೆ ಬಂದ್ರೆ ಸರ್ ಹೇಳಿದ್ರಲ್ಲ ಮೊದಲೇ
We will cover the complement of this. But we will use balls whose center in the complement of this. We will still cover this one. The centers will be here.
Yeah, so how that helps?
The reason it helps is like here, it's like this. So I try to explain here. So if I take a ball here, then I cannot deform to the center. But if the center is sufficiently far, then I can.
Star-shaped. Star-shaped.
So you can add pictures in your
Yeah.